everyone, welcome to another lecture of quantum mechanics. In this lecture, we'll discuss the normalization condition in a state which is a superposition of states. If we have wave a wave function represented by this ket vector, we write it down as a superposition of two states, phi1 ket, phi2 ket. Now, if we take an example of a vector, so I'll write it here. We write that a vector in 2D is a1 I cap plus a2 j cap. Now, why are we able to write like this? We are able to write like this only because I and j are orthogonal and orthonormal to each other. Actually, orthonormal is the complete statement. So this can be written, a can be written in form of in the form of I and j because I and j are orthonormal to each other, but the orthogonal as well as normalized. These are unit vectors, right? So I cap dot I cap is 1 and j cap dot j cap is 1. So using this analogy, like it's simply the wave functions are very similar to the vectors we have learned in our earlier classes. Okay, so keep this in mind when we are using this type of notation. So phi1 and phi2 are orthonormal. If you don't know what is what is the orthonormality condition and what is the orthogonality condition, you can look at the lecture which I given long time back. Okay, so this means that, and we also should note that the orthonormality condition or the orthogonality condition in integral form, orthogonality condition in integral form. So I'll write down both the forms, Dirac notation and in integral form as well. This one is, say you have two functions, say psi m star psi n dx minus infinity plus infinity. Now this is equal to 0 if m is not equal to n. Now this is the orthogonality condition. All right. So in Dirac notation, same thing can be written as this. Dirac notation, we write this as 0 if m is not equal to n. Now similarly, orthonormality condition which we had discussed in the previous lecture, in integral form this is written as minus infinity plus infinity psi m star psi n dx is equal to Kronecker delta 1 for m equal to n and it's 0 for m not equal to n. If we write down in Dirac notation, that is psi m psi n, we'll use the Kronecker delta notation. So this is the same thing as the orthonormality condition in Dirac notation. This is the Dirac notation. So this thing, not this one, this thing is the Dirac notation, bra-ket notation. Keep this thing in mind and we'll be using it here. So when we say that phi1 and phi2 are orthonormal, this means that the scalar product of phi1 and phi2 is 0 and phi1 and phi1 is 1 and phi2 and phi2 is 1. All right. Now the normalization condition should be, the normalization condition for psi ket should be psi inner product with psi should be 1. To get this result, we have the ket of psi, we should have bra vector for psi. So if you take a dagger, all right, if you take a dagger which is actually the psi bra vector. So if you take a dagger of this ket, you'll get the bra vector. So this is C1 phi 1 plus C2 phi 2 dagger. So this will give you the bra vector. This C1 star. Now dagger operating on C1 will give you conjugate. The C1 are C1 and C2 are complex numbers. Complex numbers. So that if you take a dagger, it will be C1 star. Now phi 1 plus C2 star phi 2, you'll get. So if you take this thing from here and apply both the things, this one as well as this one, okay, so what will you get? So you're simply just multiply this by this. So you will take the first term, we can write like this, that will replace this thing, the brass I will be replaced by C1 star phi 1 plus C2 star phi 2, and this is C1 C1 phi 1 plus C2 phi 2. If you multiply this two together, just simply multiplication, this is nothing. All right, so be careful, these are the stars, this is nothing. Now when you do this, take a product of this to this, then you will get C1 star C1. Now this is phi 1 phi 1. All right, so we have an inner product of phi 1 and phi 1. Now plus, now first we took this one and this one, and now we'll take a product of this with this. So this is basically C1 star C2, this is phi 1 phi 2. Alright, inner product of phi 1 and phi 2. Now plus C2 star, now the next product, this one with this one, C2 star, this will give you C1 inner product phi 2 and phi 1 plus C2 star C2 inner product of phi 2 and phi 2. So further, when we simplify this part, this is 1, right? So and this one is C1 mod square. All right, from complex number we have that Z mod square is equal to Z star Z. All right, so similarly we have written C1 mod square. This is 1 from normalization condition. Now this one is 0 because these are orthogonal to each other. Plus this is also 0, and this one C2 mod square, this is 1. All right, so this will give you finally C1 square plus C2 mod square. So always remember there is a mod sign here because C1 and C2 are complex numbers. So what we get finally is the normalization condition, which is equal to, this should be equal to 1. So for a superposition of state, here we had two states, so there will be two probability amplitudes, C1 and C2, and if you write, this is the normalization condition for a given state, which is a superposition of two states. All right, so we can write down that this is the normalization condition for two-level quantum system. In general, if a state is given to be a superposition of several wave functions or states, C says phi 1, phi 2 till a long list of functions, then, and we have that phi I and phi j, all these states are orthonormal to each other, phi 1 and phi 2, phi 3 and all. So there is then the normalization condition for such a state can be written as summation. See, here it was two states, so we had two terms, C1 and C2. Now here we have n number of states, so we have it, the summation will be from 1 to n, and this is the normalization condition. All right, so you should remember this form. Now what is Ci here? Ci is the probability. It's called the probability amplitude corresponding to the ith state, corresponding to the ith state. All right, now the other thing is Ci mod square. Now in some books you'll find that this is the probability of the particle in the ith state, but it's not exactly true. In some books you'll see, you will see that this is the probability of finding probability of finding the particle in the ith state. Now this is a very, you can say, a lame language to use. The best thing to say is, like, we should talk about it like this, that Ci mod square, so this is not completely correct, like, it's a very lame way to say it, but the thing is Ci mod square gives you the probability that if a measurement is made on the system, then the probability of getting the state as phi I, or the ith state. So this is what it means, that Ci mod square gives the probability that if a measurement is made on the system, then the probability of getting the state as phi I is, or the ith state. All right, so it's not like the particle is in that state, but if you make a measurement, say this has 50% chance, this is 50% chance, we'll take two states. So in that case, say if you make a measurement, then 100 times you make the measurement, then you 50 of them will give you a measurement corresponding to this state, and 50% of the times you'll get a measurement corresponding to this state. All right, so it's not like that the particle is in that state. Yeah, finally it will collapse to that state, but initially it's not in that state. Okay, so this is how you should understand it. We'll look at an example, which is psi is equal to, it's given as a superposition of two states, phi 1 and phi 2. Now this one, we are assuming that these phi 1 and phi 2 are orthogonal and orthonormal to each other. That is in terms of Kronecker delta. We are writing in terms of Kronecker delta the orthonormality condition. Let's assume that the psi is normalized, and this is, we are multiplying it by a normalization constant to make it normalized. Say this is the normalized psi. Now the normalization condition says that the normalization condition which we obtained previously in terms of probability amplitude was summation of Ci mod square equal to 1. So in this case we have two c's, so this is c1 and c2 whole square equal to 1. This is a mod square. Okay, so a square plus a square is equal to 1, which gives you 2a square equal to 1, and further you have 1 by root 2. Now if you write down the normalized wave function is this. Now this was a simple example to see how this works, how the normalization condition works. So one can also see directly that instead of going through the whole process, you can write like this, that this is c1 mod square plus c2 mod square and the given initial wave function, the unnormalized wave function. Okay, so you could have directly obtained this result by using this formula instead of going through the whole process. Now let's take up another example where we have a iota in the wave function. This is 3 phi 1 plus 4 iota phi 2. So in this case, let's assume that the normalized wave function is of this form, plus 4i a phi 2. So in this case, the normalization condition is this 3a mod square plus 4ia mod square is equal to 1. Now this is the a square will come out, and this is 3 square plus the mod of 4i will be 4 square. Okay, this is 1. Now this gives you a is equal to 1 by 25, square root this is 1 by 5. Alright, so the normalized psi is 3 by 5 phi 1 plus 4i by 5 phi 2. Right, so this is the normalized. Now you could have directly used this formula, this thing. We can see that this can be written as 3 mod square plus 4i mod square, and this is the original function. Okay, so this gives you 5, and this is 3 phi 1 plus 4i phi 2. So this is the same thing as this one which we had obtained from using this calculation. So both ways you can do it. Alright. Now in general, one can write the formula which we derived for two-state case. We can write, if psi is given by c1 phi 1 plus c2 phi 2 and so on cn phi n. Now if you want to find the normalized psi, we can just simply write down like this, root over c1 mod square plus c2 mod square plus dot 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 cn mod square, and multiply it to the original wave function c1 phi 1 c2 phi 2 cn phi n. Alright, so in condensed form we can write like this. This is root over summation iota ci mod square, and this will be summation iota ci phi I. Alright, so sum is over till n, I equal to 1 to n. So you can just remember this thing. You could use the other method also which I taught you in the beginning. Okay, so this is how you normalize a given unnormalized wave function. Alright, thank you for watching. Have a great day. If you find these lectures useful, then please like, subscribe, and share with your friends.